more than 21 billion kilometers away from Earth, far beyond every planet, and past the last reach of the Sun's influence, a machine built almost 50 years ago is still alive. It is barely surviving now, switching systems on and off simply to conserve enough energy to keep functioning. It has less power than a light bulb, and every year that power becomes weaker. Yet somehow, Voyager 2 continues to send signals back toward Earth. Before we go any further into this extraordinary story, take a moment to subscribe to the channel and help us reach 1,000 subscribers. It only takes a second, and your support helps us bring more stories like this one to you. A few years ago, engineers took some of the raw electrical readings Voyager 2 had been transmitting across billions of kilometers of empty space, and converted those readings into something humans could actually hear. When the signal was played through a speaker, something strange emerged. Something strange emerged. It wasn't a voice. It wasn't a message. It wasn't words from some unknown civilization. It was something far more subtle and, in its own way, far more unsettling. The electrical signature of the space surrounding a spacecraft that had traveled farther from home than almost anything humanity had ever built. Understanding what that sound actually represents, where it came from, and how close Voyager 2 may now be to falling permanently silent, turns its story into one of the quietest and most extraordinary chapters in the history of space exploration. The story began on August 20th, 1977, when Voyager 2 lifted away from Earth. Its twin, Voyager 1, would follow a little more than 2 weeks later. At the time, nobody expected Voyager 2 to become the spacecraft it is today. The original plan was straightforward and relatively short. It would fly past Jupiter and Saturn, photograph the planets, collect scientific measurements, and eventually disappear into the darkness once its fuel and funding were exhausted. The engineers and scientists who built it had no serious reason to believe that nearly 5 decades later, the spacecraft would still be alive and transmitting data back to Earth. But Voyager 2 was launched at exactly the right moment. The outer planets happened to be arranged in a rare configuration that occurs only about once every 176 years. That alignment gave the spacecraft an extraordinary opportunity. Instead of carrying enough fuel to travel independently from one planet to the next, Voyager 2 could use the gravity of each giant world to accelerate itself toward the next destination. One planetary encounter could effectively launch it toward another, saving enormous amounts of fuel and years of travel time. That rare alignment transformed what could have been a short mission into something nobody had originally imagined. Voyager 2 reached Jupiter in 1979 and Saturn in 1981. By then, the original mission could have ended. But NASA made a decision that would completely change the spacecraft's future. Rather than shutting Voyager 2 down, mission controllers redirected it toward Uranus and Neptune, 2 worlds that no spacecraft had ever visited up close. In 1986, Voyager 2 reached Uranus. As it passed the distant blue planet, it discovered 11 moons and 2 rings that had never been seen from Earth. Then, the spacecraft continued deeper into the outer solar system. 3 years later, in 1989, Voyager 2 reached Neptune. There, it encountered something even more dramatic, a massive storm system tearing through the planet's atmosphere, a storm roughly the size of Earth itself. Scientists eventually nicknamed it the Great Dark Spot. Voyager 2 also confirmed that Neptune possessed rings. The Neptune encounter marked another important moment. It was the last time the cameras on either Voyager spacecraft would ever be switched on. The planetary tour was over. Most spacecraft would have reached the end of their purpose at that point. But Voyager 2 didn't stop. Instead, Mission Control turned the aging spacecraft outward, away from the planets and toward the distant boundary of everything controlled by the Sun. And then they kept listening. There was another piece of Voyager's story that had been traveling with the spacecraft from the very beginning. Bolted to the side of both Voyager spacecraft was a gold-plated copper record created by a committee led by astronomer Carl Sagan. The record contained about 90 minutes of music from cultures around Earth, greetings recorded in dozens of human languages, and natural sounds including thunder, wind, and whale calls. More than 100 images were also physically encoded into the record's grooves, showing human anatomy, city streets, the structure of DNA, and other glimpses of life and civilization on Earth. Even instructions explaining how the record could be played were etched onto its cover, just in case whatever eventually discovered the spacecraft had no idea what a record was. When the Golden Record was assembled in 1977, it represented something more than science. It was an act of hope. Humanity had placed a message inside a bottle and thrown it into an ocean so unimaginably vast that the chances of anyone ever finding it were almost non-existent. Yet the record is still out there today. It is traveling through interstellar space on the same spacecraft, responsible for the strange signal that scientists have been listening to. And that becomes important later. Because while the Golden Record represents humanity's attempt to speak into the darkness, Voyager 2 eventually began doing something completely different. It began listening to the darkness itself. For most people, this is where the story of Voyager ends. They remember the pictures of Jupiter, the rings of Saturn, the strange blue worlds of Uranus and Neptune, and perhaps the Golden Record attached to the side of the spacecraft. But after the planetary encounters were finished, Voyager 2 entered the most important phase of its entire mission. The Sun, after all, isn't simply a giant ball of light and heat sitting at the center of our solar system. It constantly pushes a stream of charged particles outward into space. This stream, known as the solar wind, creates a massive invisible bubble around the planets called the heliosphere. Everything inside that bubble, every planet, moon, asteroid, and comet in our solar system, exists under the direct influence of the Sun. But beyond that enormous bubble lies something completely different. There is interstellar space, filled with plasma, radiation, and magnetic fields left behind by other stars that lived and died long before our own solar system ever existed. And Voyager 2 was heading directly toward that boundary. For decades, scientists could only imagine what the edge of the heliosphere might look like. Would the Sun's influence slowly fade away over an enormous distance? Would the transition take years, perhaps decades, as the solar wind gradually weakened? Nobody knew for certain. Then Voyager 1 got there first. In August 2012, Voyager 1 crossed into interstellar space at a distance of about 121 astronomical units from the Sun, roughly 11.3 billion miles away. What it discovered challenged the assumptions scientists had been making for years. The transition wasn't a slow fade, it was a boundary. Within a matter of days, the spacecraft detected dramatic changes. The steady presence of solar wind particles collapsed. Cosmic rays from deep space surged. The direction of the magnetic field shifted. Voyager 1 had become the first human-made object to reach interstellar space. But one enormous question remained. Was Voyager 1's experience unique to its particular path through the solar system? Or had it encountered a genuine physical boundary that any spacecraft approaching from another direction would eventually cross? There was only one way to find out. Scientists had to wait for Voyager 2. 6 years later, on November 5, 2018, Voyager 2 finally reached the same frontier. At roughly 119.7 astronomical units from the Sun, just over 11 billion miles away, the spacecraft crossed into interstellar space. And almost immediately, its instruments began confirming what Voyager 1 had already shown. This wasn't a coincidence. It wasn't simply something that happened along one spacecraft's particular path. Voyager 2 had approached the boundary from a completely different direction, years after Voyager 1, and it encountered the same fundamental transition. For the first time, humanity had two independent spacecraft, measuring the same physical edge of the solar system from two different locations. The discovery changed our understanding of where the Sun's influence actually ends. And hidden among Voyager 2's measurements was one instrument that would produce something humans could actually hear. It was called the plasma wave instrument. Its job was to detect oscillations in the ionized gas, or plasma, surrounding the spacecraft. But there was a problem. Space itself doesn't carry sound the way Earth's atmosphere does. There is no air in the vacuum of interstellar space through which ordinary sound waves can travel. So whatever Voyager 2 was detecting wasn't technically sound, it was something else. The instrument was measuring electrons vibrating back and forth and creating an electrostatic wave. These were physical oscillations in the plasma surrounding the spacecraft, not pressure waves moving through air. But there was an extraordinary coincidence. The frequencies of those oscillations happened to overlap with frequencies that human ears can detect. That meant scientists could take the raw electrical measurements Voyager was sending home, mathematically convert them into an audible frequency range, and play the result through a speaker. And suddenly, humanity could listen to something that had never been heard before. Not an alien voice, not a hidden transmission, not a message from another civilization. The sound was the physical electrical signature of plasma in interstellar space, and Voyager 2 was recording it from more than 11 billion miles away. The Sun's influence doesn't simply stop at the orbit of the outer planets. It constantly pushes a stream of charged particles outward into space, a continuous flow known as the solar wind. Over enormous distances, that solar wind creates a gigantic invisible bubble around our solar system called the heliosphere. Everything inside that bubble exists under the direct influence of the Sun. Every planet, every moon, every asteroid, and every comet is surrounded by the environment created by our star. But beyond that enormous boundary lies something completely different. Beyond the heliosphere is true interstellar space, filled with leftover plasma, radiation, and magnetic fields produced by stars that lived and died long before our own solar system ever existed. For a long time, scientists imagined that the boundary between these two environments would be gradual. They expected the solar wind to slowly weaken over an enormous distance, creating a long transition zone where the influence of the Sun would fade little by little into interstellar space. Then Voyager 1 reached the edge. In August 2012, Voyager 1 crossed into interstellar space at a distance of about 121 astronomical units from the Sun, roughly 11.3 billion miles away. But instead of finding the slow transition scientists had expected, Voyager 1 encountered something much sharper. It wasn't a gradual fade. It was a boundary. Within a matter of days, the environment around the spacecraft changed dramatically. The steady presence of solar wind particles collapsed. Cosmic rays arriving from deep space surged. Even the direction of the magnetic field shifted. Voyager 1 had become the first human-made object ever to reach interstellar space. And for the next 6 years, it held that distinction completely alone. But the discovery immediately created another mystery. Scientists had to ask whether Voyager 1 had simply encountered something unusual along its particular path through space, or whether it had found a genuine physical boundary surrounding the entire solar system. If the heliosphere really had a defined edge, then another spacecraft approaching from a completely different direction should eventually encounter the same kind of boundary. There was only one way to find out. Scientists had to wait for Voyager 2. Voyager 2 had been traveling through space on a different trajectory for decades, slowly moving toward its own encounter with the outer edge of the Sun's influence. Then, on November 5, 2018, after 41 years of travel, it finally reached the frontier. At a distance of about 119.7 astronomical units from the Sun, just over 11 billion miles away, Voyager 2 crossed into interstellar space. And almost immediately, its instruments began confirming what Voyager 1 had already discovered 6 years earlier. This wasn't a coincidence. It wasn't something unique to Voyager 1's path. Voyager 2 had approached from a completely different direction years later, and it had encountered the same fundamental physical boundary. For the first time, humanity had independent evidence from 2 different spacecraft showing that the edge of the solar system was a real physical feature, not simply an unusual event experienced by one machine. Then, in November 2019, 5 separate scientific papers analyzing Voyager 2's crossing were published together in the journal Nature Astronomy. Each paper examined a different instrument that was still functioning aboard the aging spacecraft. Together, those studies created the most detailed picture humanity had ever assembled of what actually happens at the true edge of the solar system. But one of those instruments made the story especially strange. It was the instrument responsible for the sound that had captured so much attention. The instrument was called the Plasma Wave Instrument, and its job was to detect oscillations in the ionized gas surrounding Voyager 2, the material scientists call plasma. At first, that might not sound particularly mysterious, but there was something important that had to be understood before anyone could make sense of the recording. There is no ordinary sound in space. Space is essentially a vacuum. There is no atmosphere, no air, and no medium through which a conventional sound wave can travel the way sound travels through Earth's atmosphere. So what Voyager's instrument was detecting wasn't technically sound at all. Instead, the plasma wave instrument was detecting electrons vibrating back and forth, creating what scientists call an electrostatic wave. It was a completely different physical phenomenon from the air pressure waves that reach our ears when we hear sound on Earth. And yet, nature had created an unusual coincidence. The frequencies of those plasma oscillations happened to overlap with the range that human ears can process, roughly from a few hundred to a few thousand hertz. That meant scientists could take the raw electrical data collected by Voyager 2, convert those frequencies into a range humans could hear, and send the resulting signal through a speaker. And when they did, something extraordinary happened. The invisible environment surrounding a spacecraft more than 11 billion miles from the Sun could suddenly be heard. Not because there was sound traveling through the vacuum of space, but because the spacecraft had measured a real physical process occurring in the plasma around it. The recording wasn't a message, it wasn't a voice, and it wasn't evidence of an alien transmission. It was the actual electrical signature of interstellar plasma, captured by a machine humanity launched from Earth decades earlier. For the first time, we weren't simply looking at the edge of our solar system through numbers on a screen. We could hear what the spacecraft was experiencing. It wasn't a metaphor. It was an actual, audible signal. For scientists, that distinction mattered. The strange sound coming from Voyager wasn't something created for dramatic effect. It came directly from measurements made by a spacecraft traveling through an environment no human being had ever physically visited before. Don Gurnett, the physicist at the University of Iowa who led the plasma wave investigation on both Voyager spacecraft, understood just how significant that was. When the Voyager 1 recording was first played publicly during a NASA press event in 2013, Gurnett described the moment as a landmark in space exploration. Humanity, for the first time, had produced a recording of the physical phenomena occurring in interstellar space, and the sound itself told a story. While Voyager 1 was still inside the heliosphere, surrounded by the sun's solar wind, the tones remained relatively low, around 300 Hz. Those frequencies matched the thin, hot plasma surrounding the spacecraft. Then Voyager 1 crossed the heliopause. Almost immediately, the character of the signal changed. The pitch jumped dramatically, rising into the 2 to 3 kHz range. The change wasn't random. It was the signature of colder, denser plasma surrounding the spacecraft after it entered interstellar space. The pitch had effectively revealed that Voyager 1 had crossed the boundary. And that was important because scientists didn't have to rely on a single measurement to determine what had happened. The change in the plasma wave frequency itself provided independent scientific evidence that the spacecraft had moved from the sun's environment into interstellar space. But Voyager 1 was only one spacecraft. If scientists wanted to know whether this boundary was truly part of the structure of our solar system, they needed another measurement from somewhere else. Years later, Voyager 2 finally provided it. When Voyager 2's own plasma wave data reached Earth, the spacecraft was approaching the heliosphere from the opposite side of the solar system. Its measurements told essentially the same story. Scientists detected a dramatic increase in electron density, roughly a factor of 20. The signature was remarkably similar to what Voyager 1 had recorded years earlier, even though the two spacecraft had crossed the boundary at completely different locations. Two spacecraft, two different trajectories, two different years, and yet the same physical phenomenon. That agreement made the evidence extraordinarily difficult to dismiss. Voyager 2 had independently confirmed that Voyager 1 had not encountered some strange local anomaly. Both spacecraft had passed through the same kind of physical boundary surrounding the solar system. Gurnett summarized the significance of the discovery by pointing out that the long-standing assumption about the solar wind was wrong. Scientists had expected the solar wind to gradually weaken as a spacecraft traveled farther and farther from the sun. Instead, Voyager had revealed something much sharper. There really was a distinct edge out there. It was more clearly defined than many scientists had expected, behaving more like a weather front than a slow transition between two environments. Both spacecraft crossed it within a matter of days, rather than experiencing a gradual transition that unfolded over years, as earlier models had predicted. But Voyager 2 had another surprise waiting in its data. Just beyond the heliosphere, Voyager 1 had found plasma that was slightly denser than scientists had predicted. Voyager 2, however, detected something different. The plasma it encountered was slightly warmer than expected. That difference suggested that the enormous bubble surrounding our solar system might not be compressed evenly from every direction. Interstellar material could be pushing against the heliosphere more strongly from one side than another. The shape of that bubble could be influenced by the sun's slow movement through the galaxy.